Okay, now all the guests are ready, so now we will start the second session. Dr. Noriko Yamaguchi from NARO will be the moderator of the session. Dr. Yamaguchi, please give a round of applause.
Okay, thank you. So welcome to session 2 on water management and rice heavy metals absorption. I'm Noriko Yamaguchi from NARO. It's my pleasure to serve as moderator for this session with Dr. Koji Ito from NARO. So we have 3 presentations from Vietnam, Japan, and Bangladesh, particularly focusing on the arsenic issues. So I'd like to welcome our first speaker to the stage. From Vietnam, Dr. Nguyen, Ngoc, Minh. So Dr. Minh is a professor of Faculty of Environmental Science, University of Science, Vietnam National University in Vietnam. So Dr. Minh, if you're ready, please get started.
Okay, thank you very much, and good afternoon. And it's my honor to open the second session in this afternoon. My name is Minh Nguyen, come from the Faculty of Environmental Science, University of Science, Vietnam National University in Hanoi. And very happy, this is my second time in your beautiful countries. And it's my honor to be here together with not only Japanese scientists, but also those from other countries. So my talk today is on the co-effect of climate and soil properties on the accumulation of arsenic in rice. A few years ago in my country, so we had a debate on whether the traditional feed sources or industrial feed sources contain more arsenic, and stimulated by the social media. So the arsenic issue is well known, and a lot of people, they know how toxic is arsenic. And actually, the accumulation of arsenic in rice were reported in about 2 decades ago. And we can see it as a crisis, not only for Southeast Asia, but also for many other countries, including Vietnam. So Vietnam is like in the center of parts of the belt where rice is intensively grown. And then Vietnam is now one of the biggest countries for rice exporting, and we produce annually approximately 50 million tons, and we export about 2 million tons to other countries. And with the image, so you can see on the screen, so with the cutting edge technique, so we can see the distribution of arsenic in rice grain. So it's very important to see it clearer. And let's have a quick look at how we can see the growth on the publication on rice arsenic. So I selected keywords like rice arsenic or rice arsenic, so we can see the number of publications in past 20 years. So it could be seen that the number of the publication grows so quickly, and nowadays we have several thousand publications on rice arsenic annually. And because rice feed more than half of the world population, so I was curious whether we have the different situations in different countries. What about the level of rice arsenic in different countries? And I collect the data from the previous studies in Scopus and try to build up the figure. And here we can see the overall picture on the accumulation of arsenic in rice in different countries. So we can see we have a little bit higher level in Americans, while we have less arsenic in rice in Europe or Africa, or especially in Asia. Unfortunately, I don't have the data from Japan, but it could be close to South Korea. Here's the raw picture on the right arsenic, and of course we need to have more data in order to have a more transparent picture on the one right arsenic. And because we have arsenic in rice and the arsenic comes from soil, so it's also important to have a focus on the soil arsenic. And here I have another diagram where I collected the data from different studies, and we can see the variations of the arsenic accumulated in the surface soil. One issue should be discussed and is about the source of arsenic in the surface soil. And there are two different hypotheses regarding the source of the arsenic. The first one relates to the Himalaya range. And the second one, soil arsenic comes from the mining activities. We have two biggest mining centers, one in Chile and the other one in China. So some recent studies reported that we may have the release of the arsenic from mining center, especially from China. And the arsenic can be released and deposited in the soil, in the surface soil. And anyway, it is interesting to see whether we have the variation between countries. And here, if you see the figure, so we don't have a clear trend. We don't know whether we have the arsenic from Himalaya or not, because soil arsenic in Bangladesh and in India is not so high compared to other countries like Thailand or China. And we don't know whether we have the transportation of arsenic from China as a mining center or not. But anyway, yeah, it's interesting to see and the variation between countries. And in this study, so I collected the sample through a transit from the north to the south of Vietnam, where in the north we have a very big river, Red River, come from China, and in the south we have the Mekong River Delta, where we have the sediments from many countries from Southeast Asia and China as well. And in the middle part, we have new and small deltas formed from short and small river, and it gives an opportunity to see and how different in the arsenic level in the soil form from different river system. And here, so I don't know what about your country, but in my country, so we have two different cropping seasons. So rice is cultivated 2 times a year. So we have the first season in the winter time and the second season in the summertime. And in the south of Vietnam, where we may have 3 cropping seasons, but it's not common in the center and in the north part of Vietnam. And here you can see we conducted the sampling in both seasons, in winter and in summer, and we try to clarify whether we have the difference between winter or summer season, where we have the different in the temperature background, we have different rainfall, different in humidity, and different in evaporation rate. And yeah, it could be good if we can see both the geographical changes and the seasonal changes in the accumulations of arsenic. And here's the results. So here's the first one, the first diagram. So you can see the change in arsenic in the soil from the north to the south. So we have the lower latitude and in the south, and we have a high latitude in the north. And we can see the high accumulation of arsenic in the soil of the Red River Delta in this area. And in the Mekong River Delta as well, where we have a very, very high accumulation of arsenic. Why in the central part, where we have the small and short rivers, we have less arsenic in the soil? Okay, then let's see here. So the arsenic content in the straw sample and the grain sample. So we have a similar pattern like a soil arsenic, where we have the high arsenic in soil, we have the high arsenic concentration in the straw. For here you can see for both Red River Delta and in the south for Mekong River Delta. And here we have arsenic in the grain in the winter-spring season. We have quite similar pattern between straw and rye, quite similar pattern. That means the more arsenic accumulated in the straw, the more arsenic accumulated in the rye grain. Yeah, but we have the different situation for the summer-autumn crop season, where we have different climate background. We have here for the central part, where in the winter, spring, we have a quite low arsenic in grain. Yeah, but in grain and straw as well. But in the summer, autumn season, we have a significant higher arsenic in straw and in rice. So in order to better describe the difference between the rye arsenic in the winter, spring season, and summer and autumn season, so we can use the plots. Here from the plots diagram, so we can see here the range of the arsenic in the grain is much lower than that in the summer, autumn cropping seasons. And we have the similar situation for straw. Why in the spring, winter, spring season, we have less arsenic in straw, and in summer, autumn, we have more arsenic in straw. And here we plot straw arsenic and grain arsenic. We have a correlation between straw and grain arsenic, and it's true for both winter, spring season and summer, autumn season. And here could be interesting to have here two questions. Should we shift our cropping season to what cooler periods, on what will happen in the future when we are likely suffer from climate change, from the global warming? And I like the idea that we have the difference in the accumulation of arsenic in rice relate to the difference in the climate background. So we can see here the difference in the climate background between the winter, spring, and summer, autumn seasons. So in winter, spring, we have a much lower temperature background. And in the summer, autumn, so we have a significantly higher temperature background. And another factor is the humidity. So in the winter, spring, we have a monsoon from China, and we have the high humidity. While in the summer, autumn, we have a lower high humidity. And evaporation, so in the summertime, we have more rainfall. Therefore, as the range is much higher. While in the winter, we have less rainfall, and we have a lower evaporation. And we try to look for the correlation between climate, between soil properties, and the accumulation level of arsenic in rice and straw. And we did the PCA analysis, and we tried to combine these factors for the winter, spring season, and together with the summer, autumn season. And here from the PCA diagrams, so we can see the grains arsenic is for less association with the soil and climate factor. I think it could be better if we have some association, but unfortunately, so from the PCA, we did not see it. But for PCA analysis conducted for straw and grain arsenic together with the chemical compositions of the straw. So we see the negative correlation of the arsenic in the grain with the silicon and manganese. And I think it's quite interesting to look to the association. Probably I will mention it later. And here we have a very close correlation between straw and grain arsenic. Okay. And let me talk about the mechanism, and then here a deducement for the accumulation of arsenic in the rice soil system. For the mechanism, so we should be agree that so we have an arsenic cycle in which the dissolution of the mineral like iron or manganese oxide, or the decompositions of organic matter can provide more arsenic in the soil solution. And from the arsenic in the soil solution, so it can be uptaken by the plant. On the left side, we have the rice and soil system under the warm climate. So we have a higher dissolution rate. Therefore, we have a more available arsenic in the soil solution. And we should have a higher rate of the arsenic to be assimilated by the rice. Therefore, we could have a higher arsenic level under the warm climate. On the other hand, so here, if the rice is cultivated in the cold or the cooler climates, so we have the lower dissolution rate, we have the less available arsenic in soil solution. That could be the reason why we have the less assimilations of arsenic in dry. And here, climate appears as an overall factor. It can directly affect the cycle of arsenic, and can indirectly affect the cycle of arsenic by changing the soil biochemistry and changing the plant physiology. And here I could highlight the roles of silicon and manganese. Because manganese and silicon can be attacked into rice, and it can form a physiochemical barrier inside the structure of the rice plant in order to mitigate the transport of the arsenic from the straw to the grain. Some notable remarks. We have here the longitudinal data set from the north to the south of Vietnam. So I think it could be helpful for sustainable management of rice. And here we have the comparative content of arsenic in the rice, where we have the higher accumulation level in the rice in the summer season and less arsenic level in the winter season. So it could be useful whether we can shift the cropping season to the cooler climate season in order to mitigate the absorption of arsenic. And here from the statistical analysis, so we have the strong correlation between manganese and silicon. And it could be good if we can supply the manganese or silicon into the rice in order to decrease the translocation of arsenic from the soil to rice grain. And from our geographical pattern of soil arsenic, it could be good to highlight the coastal zone as a hotspot, possible hotspot of the arsenic accumulation. And here's our ongoing campaign. So we try to look deeper into the soil structure in order to know to understand better the mechanism of arsenic transporting. Especially we use tomography techniques, so we can you can see the structure of the rice straw where the silicon is dominant. And recently we emphasize that the silicon structure of the rice straw could play an important role to reduce the accumulation of arsenic in rice grain. And we try to develop different material based on silicon and manganese and try to apply for soil in order to reduce, to immobilize arsenic in soil. And also we try to implement mesocom or greenhouse or film trial in order to better understand the co-effects of climate and soil property. And try to build up the bigger network and try to solve the issue at the larger scale. For example, not only my country, but also other surrounding countries like Cambodia, Thailand, China, or Japan. And here's some recent publication on arsenic in rice. And the last but not least, I think it's very important for us. We have to act for our safer rice. We have to act for our future rice. So thank you very much for the attention.
Thank you, Dr. Minh, for sharing us the very, very valuable results. And let's open questions and comments. I will take questions and comments from floor first, then move on to the comments from online. So, okay, please come to the mic. Please use microphone.
Thank you for your nice presentation. In your presentation, I am come from Bangladesh Rice Research Institute. In your presentation, you mentioned that silicon and manganese, due to translocation barrier, silicon and manganese, arsenic uptake restrict from rice grain and straw also. We have some study regarding silicon, but no in manganese. My question is how many kg silicon or manganese used per unit area? This is first one, and second one is during seasonal variation you mentioned summer season rice. I think summer season rice needs relatively the total growth duration lower than the winter season rice, but in arsenic accumulation both in straw and grain higher with dry season rice than the winter season rice. I think the winter season rice needs a more total growth duration. That's why the total arsenic uptake both in rice, grain and straw may be higher than the dry season, summer season rice. This is due to its second one is my clarification. Thank you.
Thank you very much for interesting question. And the first question regarding the role of manganese and silicon. So this morning we heard from the keynote speaker that the reaction between some oxidizing factor together with arsenic can play an important role to the transporting of arsenic. For silicon, so we have a large amount of silicon in dry straw. So silicon in dry straw about 5 to 10%. So the accumulation of silicon in the dry straw form so-called phytolith. Phytolith is silica structure in straw, and silica structure in the straw can play a role as a chemical and physical barrier. Yeah, because we have the precipitation of the silicon everywhere in the straw, so it can reduce the diffusion of arsenic in straw from the straw to the grain. So yeah.
Okay, this is a mechanism, but my question is, how many kilo use per unit area, either silicon or manganese? How many kilo use in rice cultivation per unit area? It's a rate, application rate, either silicon or manganese.
I have no ideas about manganese, but for silicon, so we can recycle rice straw. Okay. Then we can return the silicon in the straw into the soil, and it's very important silicon sources.
Okay. And second one is summer season rice. The temperature is high. That's why the growth duration, total growth duration relatively lower. Why arsenic uptake higher with the summer season rice?
I think we have the different situation between countries. So in my country, so in the summertime, so we have a warm, we have a high temperature, and we have a high evaporation. So we have the increasing assimilation rate.
Okay. Thank you.
Therefore, yeah, we have a higher level of arsenic in rice. But so in your countries, I don't know whether you have the higher temperature and higher evaporation at the same time or not.
Yeah, in our situation, higher temperature and evaporation rate higher in summer season rice.
Okay, so in Vietnam we have a higher rainfall. Okay. So we have the flooding condition, and we have a high temperature. So yeah, we have a
high evaporation.
Yeah.
That is the reason. Okay, thank you.
Thank you. Any other questions or comments from floor? Or okay.
Thank you for your excellent presentation. I'm Nguyen from Taiwan Agricultural Research Institute, and I'm very interested in your results, because in Taiwan we got an upside result in summer season. The arsenic concentration in rice grain is always lower than the maybe spring season or winter season, because in Taiwan the spring season is with very high rainfall. Mm-hmm. Especially the late time of the growth period, and low temperature. But the average arsenic concentration in rice grain may be 1.5 times of the summer season, because in summer season the late period of growth, the rainfall is usually much lower than the
okay, so you have lower concentration in the summertime.
The soil moisture is very important factor that will affect the arsenic accumulation. So I think it's very in research result. Maybe we need to do more research deal with the mechanism. Yes, as we know, moisture all control the arsenic availability in the soil. So in more oxidation status, I think the availability is not very high. So maybe I suggest maybe some more research maybe needed to be to elucidate more precisely about the reasons. Thank you.
Thank you very much. I think it could be interesting if we see some contrasting observation between countries. Yeah, because the effect of climate is complicated. So, but we can improve. We can measure the arsenic available in the soil solution. Yeah, but at the moment, so we couldn't measure the available arsenic in soil. So we cannot connect the effect of the climate between countries. We do not know, but it really interesting.
Okay, thank you, Dr. Minh. So unfortunately, we don't have enough time to introducing the question from the online, but so thank you, Dr. Minh.
Oh, he has a question. The keynote speaker, do you have a question? Okay, thank you.
Sorry.
Okay, thank you very much.
I'm sorry. So okay, let's move on to our next presentation. So we had time to discuss after the session. So thank you, Dr. Schumann.
Thank you.
So this is last presentation. So I'd like to thank both the speakers and the audience for providing such an interesting session and discussion. So please give a big hand to the speakers. So this session is now closed. Thank you very much.
Thank you, Dr. Yamaguchi. And thank you for participating such a long time, everyone. And now we would like to ask Dr. Tomonari Watanabe from FFTC to wrap up the first day. Please welcome on the stage.
Good afternoon. At first, I'd like to express my sincere thanks to all speakers and the moderators today. Thank you very much. Time is already 5 o'clock, so please allow me to give a brief, short, and quick the wrap up of what transpired in the first day. In our the keynote speaker, the Professor Lindquist, introduced the comprehensive review of reducing the GHG and heavy metals uptake through water management, and discuss the possibilities and the challenges of achieving the simultaneous reduction of GHG emissions and the heavy metal uptake. This report, the presentation raised important issues throughout the whole the symposium today and tomorrow. The first session is water management and the GHG emissions. From the results, of surveys and meta-analysis in many Asian countries that shows that the water management, intermittent drainage, or the AWD in rice paddies can reduce the methane emissions by 30 to 6%. The nitrous oxide emissions increase, but total GHG emissions can be reduced by around 50% in terms of the GWP. Today, we understand that the optimal water management method differs depending on the several factors, such as the geographical location, the soil conditions, and water availability, etc. Therefore, now the key challenges are how to establish the optimal water management conditions each areas, and how to disseminate and scale up those technologies in the region. The yield and the quality increase is one of the incentives for the farmers. And creating the carbon credit, the carbon credit scheme is also important approaches. The technology dissemination will be one of the topics for tomorrow's panel discussions. The second the session is the water management and rice heavy metal absorption. According to the nationwide research, Dr. Minh reported the rice tends to absorb more arsenic under the warmer and dried conditions, with soil acting as arsenic reservoir while climate influences its availability. The findings suggest that climate change could increase arsenic accumulation in rice and calling for the proactive measures to mitigate this risk. And Mr. Nakamura and now Dr. Muhammad Smong reported that the water management, intermittent irrigation or AWD can reduce the arsenic level in rice grains by up to 50%. So the water management not only conserve the water, but also mitigate the heavy metal absorption, making it viable strategy for safer rice production. Simultaneously reduction of other heavy metals, such as the cadmium, is one of the challenges. So it's very brief. That is a brief summary of the first day's presentation. And tomorrow we will have the third sessions and also the panel discussion. So please join or tuning in our symposium. Thank you for your listening.
Thank you very much, Dr. Watanabe. So tomorrow's start time is 9 a.m. and we would appreciate your feedback so that FFTC can make the best use of it in our future activities. On-site attendees can access to the question form via QR code attached to the abstract. And online participants will also receive a link by email. And to inform, a reception dinner will start at 5:45 p.m. International speakers, please meet at the hotel lobby at 5:35 p.m. Thank you very much for participating. Thank you so much.